Hello, everybody, and welcome to the first ever virtual AIPT Sci-Fi Fest. I am Jim Lehane, and I am a geologist and a paleontologist. I have a degree that's basically in geology, but specializing in paleontology. And it's what my doctorate is in, and so I have studied lots of different types of animals and lots of different types of landforms. And so the what really gets me excited is I really love geology, and I love looking at geology in pop culture. And where have we interacted with geology? Where has the general public interacted with geology and not actually understood the geology they were looking at or even realized that they were interacting with geology? And so I do a lot of writing personally and for AIPT, where I look at the geology of things in pop culture and what does it mean? How does it apply to your everyday life? Or even if it doesn't apply to your everyday life, how does it apply to the planet in which we live in, or even real science? Because we've all seen those movies where science is kind of skewed just a little, as Jurassic Park is a great example of where the science is there, but it's also a little bit skewed. So it's not 100% perfect. And that's where I find a lot of fascination. I love looking at the science that's out there, and I love trying to figure out what is possible. What of the movie, TV show, or various other things, what is possible in that world that the authors or the directors or whoever created? And so there's a lot of geology in Star Wars. You're looking at entire planets. There's a lot of biology and science and all that sort of stuff as well. And so when you break it all down, there are countless things that we could talk about. Like, there's been hundreds of hours of TV shows for Star Wars. There's how many movies now? 11 movies. And so there are a lot of things that I can pick apart and just kind of geek out on. I geek out a lot on the science. And so I was going to limit what I talked about today to just a couple of items, because these are the things that I find super fascinating, and I'm hoping other people will as well. And so the first thing I'm going to talk about is when I was sitting in the movie theater and something popped up on screen, and I just almost jumped out of my chair. I was so excited. It was during The Last Jedi, and they're on this planet Crait. Towards the end of the movie, they land on these white plains of something, and they all get into the bunker, and they have to start to defend themselves in the battle. And during that battle, they are in a trench where one of the characters notices that a boot print is left behind, and it leaves a red print. Basically, there's a red crust of something underneath the white overall crust. And he reaches over and he touches it, and he kind of licks his finger and goes, salt. And you can tell that they tried to put a little cameo here, because Gareth Edwards, the director of Rogue One, was the person next to the guy who did the little salt bit. But what got me super excited is that we all know salt. Salt, NaCl, sodium chloride, is common table salt. It is actually also a mineral. A mineral is a geological term for something that has a set structure and set properties of different substances on Earth. And salt is one of the more common ones that we use because we use it in our food. And so you know the taste of salt. And this mineral known as halite in geology is one of the more common industrial minerals. But there are related minerals. There is a different type of salt, it's a cousin to halite, called sylvite. And sylvite is potassium chloride, KCl. And it is a very bright red color. And so I was super excited when I saw all this red salt on the planet, and I went, oh my god, they made a planet full of sylvite. Even when they're flying the Millennium Falcon through the caves, it looks like salt crystals. And that just got me super excited because, like, this is something, although maybe not intentional, it can be related back to actual science. The Last Jedi actually also has a fossil that's very, very briefly seen when Rey's doing her meditation. They're kind of going through the entire Earth, and you can kind of briefly catch a fossil within the middle of the ground. That's kind of cool. I haven't actually stopped and examined what it could be, but that's one of those things that is like a little nugget, a little Easter egg that is there for people to later check out. But there are real fossils in Star Wars, and it goes back all the way to the original Star Wars movie that came out in 1977. If you remember, when R2 and C-3PO land on the planet, they're walking through the desert trying to find anything. There is a skeleton way off in the background, and that's always been called a Crait dragon skeleton. And that's basically what they used to develop the Crait dragon in The Mandalorian, something like that. Crait dragon has been used in lots of other stories that doesn't really match with what that skeleton looks like, but the Mandalorian actually is probably the closest thing to what a animal that had that kind of skeleton would look like. But that skeleton in particular came from another movie, and that movie is called One of Our Dinosaurs is Missing. We found it. It's in the desert. It actually is still in the desert. When they went back to Tunisia, where they filmed those scenes back in 2002, that they were still uncovering parts of that skeleton. And normally, when you have a dinosaur on display in a museum or any type of display, most dinosaurs that you see are not the actual fossils that were found. They are casts of those bones, and there's a lot of reasons for that. One, the bones that you find as a fossil, they're very, very heavy. They're actually rock. The rock in the shape of the bones is, over time, the bones get replaced with minerals, like we talk about minerals again. The bone gets replaced with the minerals, making the bones into rock. And those rocks are very, very dense. They are very, very heavy. And so the larger the animal, the more weight that it has. And some of these animals are so heavy, the fossils that these bones are so heavy that they really don't allow for easy movement or displaying the animals as we see them in the museums today. And so what scientists will do is they'll make a cast of those bones, a replica of the bones, and those casts are what we see in the museums. The casts are a lot lighter, and you can actually put the mounting, usually metal armature, within the bones themselves, making the cast stand out a little more so you don't really see all the metal holding up the bones. And so you can actually tell the difference really easily when you go to the museum. If you don't see the bones, or if you don't see the metal armature and it runs through the bones, those are cast because you don't want to destroy the fossils. But if the metal armature is actually cradling and holding the bones, then those are going to be real fossils, because you don't want to drill holes into the fossils. You want to be able to preserve them, but also the way that they hold the bones in some of those armatures allows scientists to come and take them out and do studies on them, whatever kind of measurements or studies that they would need to do for that particular bone, for that particular animal. And so what they had done is, a lot of time, if you have a kind of a unique animal or a really well completed animal, well preserved animal, is they'll take a lot of casts of that particular animal and they'll sell those casts. That way the museum can make some money, or whoever happens to own the casts for that animal can make some money by selling it to other museums, and then other museums have something to display. And so you have like maybe a couple of T-Rexes on Earth, but you have every museum has a T-Rex skeleton, and that's because those couple of T-Rex skeletons get sold off as casts to the other museums. Well, that is what happened here, is that we had a cast of a Diplodocus, one of those large, you think of Brontosaurus, something very large. Diplodocus looks kind of similar, has more of a really long tail, that whip-like tail, and a rather long neck. Well, they had several of these casts. One of these casts made it to the Disney Studios lot, where one of our dinosaurs is missing was filmed, and that is generally at least part of it was used for the animal in that movie. The skull on that cast is absolutely atrocious. It's not anywhere near the actual skull used in real life, or that Diplodocus had, but most of its neck vertebrae are from the real cast. And so after that movie, Disney Studios owned this cast. Eventually it made its way over to the Star Wars set, where Lucasfilm apparently got a hold of it for the original Star Wars, and that is what you see in the background of A New Hope. It's actually a cast of a Diplodocus that has the loving nickname of Dippy. And so I found that one of the super cool random facts is that there is actually a dinosaur in it, and actually there is another dinosaur kind of in the movie in a sort of way, in the special edition of A New Hope, as they're driving into a Mos Eisley, they run across a Ronto that's kind of rearing back up on its hind legs, and the little Jawas are dangling from the ropes. That Ronto is based on the Brachiosaurus that we see in Jurassic Park. When you see they first arrive on the island and they're looking at the dinosaurs, you see the Brachiosaurus kind of rise up on its hind legs. That same model, since ILM did Jurassic Park and also does Star Wars, that same model was then used, kind of shrunk down, but generally that same type of the model was used in the special editions of A New Hope, and that's where the Ronto comes from. It is actually a miniaturized Brachiosaurus. One of the more geological aspects of the movies is when you fly around the galaxy, there are several planets that have entire planet encompassing what we call biomes. Everything is a forest, everything is a desert, everything is molten rock, or it's all an ice planet. And so when we look at our own planet, we don't see that. We see areas that are covered in ice. You see areas that are volcanoes. You see areas that have a lot of forests. But we don't have these all-encompassing biomes across the whole planet. Not now, at least. A long time ago, about 700 million years ago, our entire planet used to be covered in ice. And it is a theory, but a really well grounded theory, called the snowball Earth theory. And what that means is that at one point, our entire planet had glaciers, or ice, entirely encompassing it. And the way that scientists know this is that glaciers leave special kinds of deposits. When a glacier moves through the Earth, you have this giant sheet of ice, and you can see this now. We have glaciers on the Earth now in Antarctica, Greenland. I went up and saw glaciers up in Canada. Near there's a national park called Jasper National Park that you can actually walk up and drive onto one of the glaciers. And as a glacier moves, it actually moves because at the top of the glacier the snow is falling, and snow continues to fall because it's rather cold there, and it builds up over time. And as that snow builds up, it starts to get compacted on the bottom, and that compaction squeezes the snow into ice. And more snow keeps falling because it never gets warm enough to melt. And so the snow keeps falling on the top, more ice and more ice builds up. And eventually so much ice builds up that it starts to actually flow outwards from that spot. And most of the time, these glaciers are formed on mountains. So instead of flowing out in all directions, it flows out downhill. And And so the heavy ice, or the thick compacted ice on the top of the mountain, the hill, pushes the snow and ice down the hill, and you get to a point eventually when it gets to be too warm down the hill, and that snow and that ice will melt. Well, as this glacier moves down the mountainside, it actually will pick up rocks, it'll pick up soil, it'll pick up anything on the ground, and it'll act as a giant piece of sandpaper, because all those rocks and that soil will get embedded in the ice. It'll start to defrost and it'll freeze again, and you'll have basically a giant piece of sandpaper on the base of this glacier, and it'll slowly scour away the ground underneath the glacier, and all that stuff gets bunched up and captured inside the glacier. And as it's moving, it's still carrying with it all that rock, all that soil, all that other stuff that's mixed in there until it gets to the end. And when it gets to the end, it actually will start to deposit the stuff, kind of like a conveyor belt. As it carries everything along, it'll drop everything at the end in a giant pile. And that giant pile is called a moraine. We can see moraines nowadays. There are moraines all over the place. They are basically just piles of debris. They have a lot of clay in them, and that's kind of what differentiates them from a lot of other geological features, is that this has a large amount of clay, because as that stuff is getting eroded across the ground, that the rocks kind of powder the other rocks that it's riding over, and so you get a lot of that powdered rock flour, it's generally actually called. And these pile of clay, boulders, sand, and everything is unusual, because when things fall in water, if you ever mixed up a bunch of sediment in water, it'll actually settle out into different layers. Heavy stuff, the large stuff will drop out first, and then the smaller stuff, the sand, and will come out, and then the clay will eventually settle down. And so you'll actually get a gradation of sediment sizes, large on the bottom, smaller, up to the smallest on top. That is how water will separate out sediment. Meanwhile, what we see in the glacial moraines is everything's mixed all together. And this material is called till. And glaciers are unique in the way that they deposit this stuff. So we know when we see a glacial deposit. Well, over time, the continents have all been moving around. We can generally backtrack where the continents have been when, based on what fossils are in there. We know what the climates have been. We know how the continents are moving today, and so we can kind of work them back a lot of times. But when scientists started to do that, they got to a period around 700, 800 million years ago, or 6 to 800 million years ago, when they're looking at the rock deposits, and they noticed the till. They noticed these moraines. But these moraines were in locations that would be considered the equator at that time. And the only way to get moraines is through glaciers. And if you're on the equator and you're getting glacial deposits, that means that ice is on the equator. And if ice is on the equator, it's everywhere. And so that kind of leads to this theory that at one time the Earth was completely covered with snow and ice. And so we had our own mini Hoth. Now this is before any land animals had evolved, and so we don't have the mammoth. We don't have the tauntaun. Love the tauntaun. But if this were to happen again, we would have our large animals. And we have gotten closer to a snowball Earth type of thing in our ice ages, where again the Earth is covered with like caps of large regions of ice, much less than a snowball Earth, but much more than what we have today. And so the way it kind of works is that white surfaces reflect sunlight, dark surfaces absorb sunlight, the water absorbs sunlight, absorbs energy. The more snow you have, the more surface you have that's reflecting sunlight, so the Earth doesn't get as warm. It's reflecting a lot of that heat, and so the Earth can kind of cool down. So you have more snow, you have the Earth cooling down, causing more snow, and the Earth cooling down. It's kind of like a runaway train effect, where as the Earth gets more and more snow covering it, eventually more and more of the Earth gets covered in snow because it gets cooler and cooler and cooler. And the opposite works, where the less snow you have, the more light can get in, the more the water, the oceans can heat up, and the warmer it gets, and so you get less snow, and kind of works its way in reverse. And so we have a lot of these runaway train effects where the Earth gets covered in snow, and more snow, and more snow, and eventually that gets reversed. How does it get reversed? Scientists aren't entirely clear on how it gets reversed. A lot of the theories have to do with carbon dioxide, something that we know today as a greenhouse gas, because as humans we are pumping it into our atmosphere and we are making our Earth warmer. Well, there are other things that put carbon dioxide into the atmosphere. We know volcanoes do a lot. And back 600, 700 million years ago, when you have nothing else on the planet except for snow, you still had volcanoes being active. And those volcanoes were spewing out carbon dioxide into the atmosphere. And over a long enough period of time, a lot of that carbon dioxide could build up, creating an atmosphere that was warm enough to slowly reverse the effects of snowball Earth. Scientists don't know this for certain, but it is one of the leading theories on how we kind of got out of it. Because as you can see, we're not in a snowball Earth anymore. We have green fields, we have trees, and we have summer and spring. And fall, actually. So, that is kind of our own Hoth. We did used to have a planet that would be Hoth. We also have other areas of the planet where large regions are covered in desert. We don't have a desert-sized planet, but it is theoretical that we could, or another planet could, especially like when you look at Tatooine, it has 2 suns. That's going to be a lot warmer than our planet, which only has 1 sun. And so when you have a degree of warmth to that degree, you're likely going to have less available water as it gets evaporated into the atmosphere, because the sun is really your driving force of your climate. And so with the sun there, it's going to evaporate a lot of the water that's out there. But we did have lots of large regions of our planet that were deserts. We look at the Sahara today. Sahara is one of the largest sand seas that we have today. Kind of what you would see on Tatooine. A sand sea, the technical term for a sand sea is called an erg. One of my favorite random geology words is erg. And that's basically what you see, is just the rolling sand dunes like in Tunisia. We did have a erg in North America, where I live, that used to be a lot bigger than the Sahara, like many, many times bigger. It's called, it was the Navajo sandstone is what is the remnant of that erg. And that Navajo sandstone was probably covered an area that was like 2 to 3 times bigger than the Sahara. And so we do see representations of these large areas, and we don't really know Tatooine that well. We've seen Mos Espa, which we assume is fairly close to Mos Eisley, but they're both relatively in the same area, since we know that Cliegg Lars went to Mos Espa to get Shmi, and then you can get to Mos Eisley from the Lars homestead. So they must be relatively fairly close, but we don't know where the town that the Mandalorian had ended up going, Mos Pelgo. We don't know where that is related to anything else. We know it's quite a bit of ways, but it could be still fairly close by, that it would be within the same system, or the same biome. And beyond that, we could be dealing with, they may have ice caps. They may not. Seeing it from space, you generally don't see any of that, so it could be a planet completely covered in ice, but maybe it wasn't at one time. And that's one of the things with these one biome planets, is that we're seeing them at one time in the movies. We don't know how things have changed through the history of the Star Wars universe. And we can't make assumptions that this didn't happen. And so that's my favorite thing to do, like I said before, is to find out, well, how does this work? How does this work in the science? We look at Tatooine, we see the pod races go through caves. Caves need water, generally. And so, where did the water go? Was it ever there? Were those caves formed from water? And so, things like that are what gets me super excited about this. And that's why I hope that I imparted a bunch of sciencey knowledge about the Star Wars universe. There's hours more things that I could talk about and that there are out there. But I'll leave you with those, and I hope that you enjoyed. You can hear me on our AIPT's Star Wars podcast, Talking Tauntauns, at any time. And enjoy the rest of the convention.